Hi, this is a re-recording of an IC Mentor WebEx that was actually done last week. We had some issues during the recording that only appeared as you're doing the WebEx in terms of the PNIDs that I had constructed being distorted. So I saved them out as pictures, and I think we should be okay. And we'll do the recording here to allow you to see it again and listen to it again, and hopefully share it with a lot of other people. So temperature measurement and control is a very important subject because temperature is perhaps the most critical measurement in terms of process efficiency and capacity. We know it affects energy usage, but it also is very important for product quality and production rate because temperature is closely related to reaction rates and to possibly side reactions that might occur in undesirable products. It's also important for purification, distillation, and there may in fact be an inferential measurement of composition. This is very common in distillation column control, as we will see. So we want to get the best possible temperature measurement in terms of accuracy and responsiveness, and then we want to come up with a control strategy that makes the most out of that to improve the process performance. You probably know me quite a bit from my publications, but I encourage you to go to the Control Global website where I have my Control Talk blogs and my Control Talk columns actually for the last 14 years. Actually, they're only online maybe for the last 12 years. But anyway, there's quite a collection there of terms of interviews, giving you the expertise of a lot of different people in our profession. Also, you get to hear my perspective on things, and particularly in terms of the Control Talk blogs. And then for the IC Mentor program, we have a website where we have questions and answers, and we try to make the most out of the conversations we get between the proteges and the resources. And I try to also do publications and presentations that allows us to share that conversation and also give the recognition that's long overdue to many of the people in the automation profession. Well, one of the things I like to do is to break the ice and open minds with some humor, or what I think is humor, but often it's hopefully a little insightful. So here's the top 10 things you don't want to hear about a temperature loops. We partially withdraw sensors and thermal wells to get a smoother response. I actually had a very smart biochemist show me this, and he was very proud of what he thought was then better temperature control of his bioreactors. And not knowing he was really just getting a very filtered temperature from the air that was in the thermal well. Of course, if you took the sensor completely out, it might be even smoother. We installed transmitters in the I/O room for coordinated maintenance. Boy, these were very accessible and got a lot of attention, and they probably needed more attention because of the errors introduced by the extension wire. Number 8, we installed sensors near the E&I shop for quicker maintenance. Well, then we got all that transportation delay, and boy, if there's sample lines, we've got also, besides the incredible delays, the poor velocity that we're going to talk about here is being really detrimental. We save money by going to thermocouple or an RTD input cards. Well, and we'll see how much better off going with transmitters. Today, with the new DCS input cards that are much smarter and more accurate and higher resolution, it's less of a problem, but we'll talk about how it's still desirable to have transmitters. We use clamp-on sensors to avoid the cost of pipe nozzles. I know this is attractive, and boy, it looks really cheap and easy. Well, often what's cheap and easy isn't what's best. We standardize on thick, short thermal wells to prevent vibration failure. You know, some of the things that are out there in the literature that's most publicized and documented is this concern of vibration. Well, yeah, we want to make sure we deal with that, but not to the exclusivity of all the other issues. And if we go for um, you know, maximizing our resistance to vibration, even to absurdity, we're going to cause a lot of problems in terms of the response and accuracy of the temperature measurement. He made all the temperature measurement scales the same. Well, yeah, that might help in terms of things being more replaceable for transmitters and maybe more recognizable in terms of what you want to do. But you're going to have to end up doing more because of the errors introduced as percent of span are then actually maximized. The controller reset time is smaller than the controller gain. Unfortunately, this has happened, and we'll get into that. And boy, if you ever see a reset time, particularly, well, even seconds or minutes per repeat, that's smaller than a controller gain, we got problems. We choose a column tray for control that always drew a straight line. Well, straight lines are very attractive, but you don't want them if you're using temperature as an inference of composition, except after maybe it's on control, but not as you're making tests. The controller input and output are drawing a straight line. Well, some process engineers have asked me to do that, but if that's the case, really the controller is not doing anything. There are disturbances just by the nature of things. That's why you have a controller. And so what you do is you transfer variability that's in the controller input to the output through feedback control action, sometimes feed forward action. And so necessarily you can't have the output also drawing a straight line long term. I mean, short term that can happen. You're at a steady state and things are quiet, but in general, the controller's got to do something, and what it does is change its output. Okay, let's look at some key things about the three different types of measurements that are mentioned, although I have to admit that I haven't used thermistors very much, and so all I'm going to do is kind of give what's been cited in this source. The source is actually dates way back, but boy, it's one of the best ones in terms of being very comprehensive in terms of key performance characteristics. And first of all, let's look at repeatability. That's incredibly important for any sort of control system. That if you get a change in the process variable, you're going to get the same sort of change each time. If it's erratic, then like how the heck does the controller deal with that? So repeatability is incredibly important, and we see that for the thermocouple, the repeatability and this might be for large changes. It could be 1 to 8 degrees centigrade, much larger than I would have expected. Whereas for platinum RTD, it's an order of magnitude or more less. It's also pretty darn good for a thermistor, but not as good as for an RTD. Then we get into drift, and for thermocouples, the degrees C per year can be 1 to 20 degrees. Hopefully you never even get anything approaching 20 degrees. That often occurs at very high temperatures. And compare that to the RTD, and not only is the drift so large for the thermocouple, but it's very unpredictable. If we knew that it was going to drift at a certain rate, we could probably do something smart about it, but we don't, and it may stop drifting for a while, and then it may accelerate drifting, so it's really very problematic. And down here at the bottom, there's a note that operations may change the set point to account for the offset from drift. And after it's been drifting for a month or even a year, they say, well, hey, this distillation column's not doing as well, and they You know, they try, well, maybe I'll, change the set point. Oh boy, it's working better now. So then they go with a better set point. Hopefully that information gets transferred from one shift to the other. But then what happens when that sensor has been changed or the drift changes? Well, now you have a problem in terms of, what is the right set point, and you're always trying to play catch up at best through trial and error. Not a good situation. So the drift is unpredictable, and the replacement of the sensor causes an error in the operating point, particularly if you've changed the set point. Now look at the sensitivity. Sensitivity is good for the thermocouple, but how much better is it for the platinum? And here we see the advantage of a thermistor, incredible sensitivity. Now the benefit we get from the thermocouple here is in terms of temperature range, and it is huge, and we have to go with thermocouples for very high temperatures. The temperature range for RTDs these days is much higher than what I'm used to. I know, but this was about 20 years ago where we got into trouble with temperatures that were around 500 degrees C to RTD insulation sheath errors. I think they've made improvements in the sheath design, but they do acknowledge that if you get above 400 degrees C, you're going to increase the errors in the RTDs. So the values we see here in terms of repeatability, drift, and sensitivity are all probably based more on being below 400 degrees C. So you have to be careful once you get above that in terms of really how well you're going to be doing. And that's this big note here, note 1. You can get into significant errors, and I don't have good information right now on that above 400 degrees C. So this statement now that you can use RTDs up to 850 degrees C, you have to be careful about that because in our case, and again, that's 20 years ago, we had to go back to thermocouples because the error was so large. And the temperature range for thermistors is not that great. Signal output is problems with thermocouple. It's low, and so it's more vulnerable to signal noise. Here we see that it's orders of magnitude larger for RTDs, and it's pretty large for thermistors. And I think there's probably a 0.01 or 0.02 missing here in this column. The power is low for thermocouples, and here we see, boy, it's four orders of magnitude or more larger. And it's even larger here for thermistors. Minimum diameter in terms of millimeters, this is not inches, but as millimeters, you can get an extremely tiny thermocouple if that's what you need. But in the process industry, we don't tend to see that sort of a requirement. So the minimum diameter in millimeters of 2 is fine normally for an RTD. Linearity is good for a thermocouple, excellent for an RTD, and for the thermistor is very poor. But these days, with smart computing devices and input cards, they probably have a way of dealing with that. The other thing, as noted here at the very bottom, is that the RTD transmitter sensor matching by entering constants into the calendar Van Dusen equation that's in, say, a smart transmitter. And now I find out it's also in some smart RTD input cards for the newer I/O systems of distributed control systems. They can improve the RTD accuracy, which is already darn good, by a factor of 5. So it's very attractive to enter those constants for the what we abbreviate or use an acronym for CVD, and that's my acronym. Not sure you'll see that elsewhere, but it's the calendar Van Dusen equation. Let's look at the bare element speed of response. So one of the things that said you got to or you should be using a thermocouple is that it's much faster. Well, yeah, you look at the bare element response and you're looking at a very tiny element like For me, tiny, eighth of an inch. Yeah, it's really fast. However, you get into the larger sizes that we normally would consider, and particularly if it's not grounded, we're getting up to 4.5 seconds. Now we start looking at the RTD. Yeah, it's slower, but you know, if you're starting to compare the quarter inch, and particularly against the one that's ungrounded, in other words, insulated at the tip, it's not that much different. Um, and the other thing you got to consider is whether you really should be using dual elements, and then you're going to get into larger response times, but you then have a backup right there built in terms of another element. But we hardly ever, or I have hardly ever used bare sensing elements, and for good reasons. They're considered unreliable and unsafe in the process industries. A thermal well provides the personnel protection and prevents chemical and physical damage by isolating the sensor from the process. This is very important. So I think this whole thing and focusing on bare element response really is somewhat misleading. We ought to be looking at the response from the thermal well. And that's what we're doing here. We're looking at the response in the thermal well for different types of processed fluids. And first of all, we look at gas, and we have higher velocities typically for gas, and we're looking for annular clearance in terms of inches in this case, and the type of fill. Normally it is air, and we can see that we get into some very high time constants if we consider the thermal well itself. And notice that there's two time constants, which is kind of typical for temperature responses, and there's a large one and then a small one. And you can almost add these two up to get the effect in terms of additional lag and delay on the control system. So you can see how adding oil is going to make a dramatic difference. If you can reduce the clearance inside the thermal well, you can make a dramatic difference as well. Now, this is an exceptionally tight clearance. I don't know how practical that is. I guess if you get into temperature changes, it could be difficult removing the sensor from the thermal well due to just expansion, possibly of the element itself. Inside the thermal well. So you look at then at liquid process responses, and you see that the velocities are quite a bit lower. That's just the way it is in processes, and we see that we get into some very large time constants for some very low velocities. What we'll see when we get into pH measurement control, the effect is actually much more dramatic in terms of low velocities for the pH electrode response. Here, it's important, but maybe not anywhere near as problematic because, you know, often in an agitated vessel, unless you have the thermal well sticking pretty close to the impeller, the fluid velocity is probably around 0.1 or 0.2 feet per second. And we can see here that with kind of a typical clearance, we're getting response times that have a time constant of 32 and 10 seconds. So we see how much larger that is than the bare element. Now we increase velocity, and we can see that we can reduce that significantly. And then if we use oil. And the problem with oil is at very high temperatures and get sticky. And then you have to make sure also that the oil is in the tip. So, you know, if you have it installed horizontal or if you have the tip pointing upward, that's going to be, of course, a problem. Then as you get into very tight clearances, very large clearances right here, it gets huge in terms of the time constant, incredible. So sloppy fit or something that's partially withdrawn is really problematic in terms of a huge time constant. And then if we get into a very tight fit, we can see how we can kind of approach what the bare element response is. So there's many thermocouple advantages stated. Are they real or perceived? But if you examine them closely, you realize they're not as important as you might think. Thermocouples are more rugged than RTDs. However, the use of a good thermal well protection tube design, installation methods make an RTD sturdy enough for even high velocity streams and some nuclear applications. It used to be that maybe they were considered they couldn't be used in nuclear applications. Now they say they can after they've looked at it more closely, and this is something that's happened in the last 20 years. Thermocouples appear to be less expensive until you include the cost of the extension lead wire, the cost of process variability from less sensitivity, and less repeatability, and the cost of a poor operating point due to unpredictable and significant drift. Let's look at some installation details here, and we've got different types of heads. We use the extended cover head most often, and also the union nipple to ease for disassembly of the thermal well head, and to get at the element and be able to take it out and test its calibration. And we usually used flange connections as being the one that was most reliably installed, and also probably was in some ways easier to get out, certainly than some threaded ones that got corroded or due to thermal expansion caused tightening. There's a conduction error that's very important to make sure you minimize, and that's due to the thermal conductivity of the well itself and the heat flowing along the thermal well. If the temperature inside in the process is higher than outside the pipe, which is what I often think of, then you got this heat flow from the tip of the thermal well out towards the flange or the connection of the thermal well. And if you have low conductivity material, then there's more of a problem in terms of the conduction error, because of what you're seeing is less of the response to the process temperature inside. And we see that for metals, like stainless steel and cast alloys, they're pretty much similar. You get into carbon steel, which is kind of unusual. I guess brass could be for water streams, not that unusual, but you get into problems. Not shown here is when you have protection tubes that have low thermal conductivity, then boy, you really got a problem, and that's why I really don't like to see ceramic protection tubes. Hopefully there's some alternative to that because of the low thermal conductivity of the ceramic. Here we look at the insertion lengths for different types of thermal wells: straight, stepped, tapered, and recessed. And we see that the stepped is the best, and the next best is the tapered, in terms of minimizing the susceptibility to vibration failure, and shows you how you can as the velocity goes down, how much greater length you can have in terms of the thermal well. Now we want the greater length to minimize the conduction error and to make sure that we're getting a representative measurement right in the most representative point in the process. And we don't want to be measuring the vessel wall temperature or the vessel jacket temperature or the pipe wall temperature or the pipe jacket temperature. We want to be measuring the process temperature. So we want the length long enough to do that. But then we got to worry about vibration failure. And so here we're seeing that the stepped and tapered help reduce vibration failure. And they also turn out, because of the smaller diameter at the tip, they turn out that they're actually going to reduce the conduction error. So you get more accuracy and a faster response for these types of thermal wells. So here we looked at the fact that if you got a recessed thermal well, naturally the conduction error is going to be larger. And you can see how the heat transfer coefficient is going to affect it. So you want to maximize the heat transfer coefficient so that the error from conduction is minimized, and the way you can maximize heat transfer coefficient is by a higher velocity. So we not only reduce conduction error, but as we saw before, the higher velocity allows us to have a faster response time. So if we don't have the higher velocity, you're going to have to go with a longer insertion length, and then you get into concerns about vibration failure too. So I would like to see more attention paid to this, and to kind of complement what we have in terms of a lot of attention about vibration failure. The thermal well tip should be in the center of the pipeline. To reduce cross-sectional temperature profile errors from the wall and due to poor mixing, and to maximize the velocity, which is usually greatest near the center of the pipeline, with enough length to reduce the conduction error. And you can achieve that in an elbow, even for, we got a small diameter pipeline. So here we show that this is the best choice. Then the second choice, I mean, man, it's got problems in terms of maybe vortices causing some erratic temperature fluctuations, reducing uniformity. So it's not as desirable as the number one choice here of having a point right in. Then you get into these others where you really don't have a tip near the center, and you don't have enough insertion length. And so here, by angling it, you can do a little bit better. And the worst situation is number 4 here, where the tip is not at the center, and you have a very short insertion length. So not a good deal. And the error seen for installations 3 and 4 is so large for polymers that I've seen where the measurement may be more of a pipe jacket temperature rather than the polymer temperature. And there's an incredible temperature profile associated with polymers. I think it's partly due to the high viscosity there. And so you really have to get close to the center line of that polymer pipe to get a representative temperature, and then you really need a lot of insertion length there. So it is a real challenge, particularly for polymers, high viscosity fluids. Now, for heat exchangers and static mixers, the concern is that as you come to the outlet here, you get a recombination of flows in kind of a flow profile that's kind of erratic, and so you want that to kind of stabilize. So it's best to have about 25 pipe diameters before you try and have a temperature measurement, and then ideally it should be an elbow again. So the optimal location provides good velocity, sufficient mixing, and minimal time delay. So for this reason, you don't want it 100 pipe diameters. You might get a little bit better mixing then, but you've got quite a transportation delay, because the transportation delay is the volume between the outlet of the equipment and the sensor divided by the flow. Now, if you really have a problem in terms of sensitivity to mixing, you might have to go and accept a higher dead time. And then there's some things we might be able to do in the control strategy in terms of dead time compensation. but that can be a little tricky. For D-Super's sensor installation, we're dealing with two different phases here, and we're trying to minimize the water droplets that might be in the steam as they're going to the sensor. And so there are some guidelines. There's actually calculations that can be done, which I encourage you to have your supplier do using their computer programs that are very intelligent and take into account a lot of details. But here we're just kind of giving you an idea of the significance of what we're trying to do. For D-superheaters, the distance from the outlet to thermal depends upon the performance of the D-superheater, process conditions, and the stream velocity. To give it a feel for the situation, there are some simple rules of thumb for the straight piping length, SPL, to the first elbow, from the outlet of the superheater to the first elbow, and then the total sensor length, TSL. The actual SPL and TSL values depend upon the quantity of water required with respect to the steam flow rate, temperature differential between water and steam, water temperature, pipe diameter, stream velocity, model type, etc., and are computed by software programs. But here we have some rules of thumb to give you an idea of what's going on. The SPL in feet is approximately the inlet stream velocity in feet per second times 0.1, which is the seconds of residence time needed as a minimum. The TSL, the total distance to the sensor, is the inlet stream velocity times 0.2 seconds of residence time. So you can get a kind of an estimate as a check. Typical values for inlet stream velocity upstream the superheater range from 25 to 350 feet per second. So the velocity is quite high. And so you can get into some distances that are pretty appreciable. Below 25 feet per second, there is not enough motive force to keep the water suspended in steam. So if you got that situation for some strange reason, you got a problem. If velocity is higher than 350 feet per second, causes the superheater to vibrate and damage the unit point where it can break apart. So that's a safety besides a reliability concern. Well, let's look at temperature control strategies. Now that we got the best temperature measurement, let's look at how we use that in control strategies. And a very typical problem is a vessel jacket, where we've got a temperature we're trying to control for that. Typically, there's a temperature controller with a set point coming from the vessel itself. But here we're just looking at the jacket temperature control, and we're going to look at inlet temperature control and it's manipulating a makeup cooling tower to water flow. This is very important that you're manipulating a makeup flow because you want to keep a constant recirculation flow through that jacket. It eliminates the increase in process gain and process dead time at low coolant or heating demands, providing better tuning and performance. And what's not recognized is that it's also preventing this burst of oscillation people often aware don't realize can occur at low utility flows. That is very confusing to people due to a combination of a great increase in process gain and an increase in process dead time. If the recirculation flow is being throttled instead of a makeup flow, or changing the temperature rather than the flow rate coming in here. So we're changing the temperature by manipulating a makeup. The jacket inlet temperature control offers faster correction of jacket utility disturbances. You see the disturbance quicker at the inlet here because that's where it's coming in before the inner jacket, and because the loop dead time from transportation delay from here to there is less. Limits can be placed on temperature set point also here to prevent cold and hot spots, and that can be important for crystallization. It's also very important for bioreactors where the cells are very, very sensitive to localized cold and even more so hot spots. So you want much greater uniformity there. Also got shown and here at the very top in blue is the fact that you can do an inferential measurement of reaction rate and really its conversion rate. And that's based on particularly an exothermic reaction in terms of the cooling rate. And you can get the cooling rate by taking the inlet temperature and then having having that subtracted from the outlet temperature, and that gets you the differential temperature, and that combined or multiplied by the recirculation flow, which is hopefully constant, can give you an inferential measurement of the conversion rate. Now, to get the synchronization of the inlet and the outlet, you have a simple dead time block, and its dead time is the transportation delay. Again, another reason why to have a constant jacket flow, so that that's a constant setting here. This is very good for continuous operations to detect fouling going on or some conversion rate problem, but you can also see for a batch operation how important this is, because it's telling you when the batch is approaching completion, the conversion rate's going to zero. And if it comes back up again, maybe something undesirable is happening. The batch should have been terminated. Now, a lot of processes say that they want the jacket temperature control to be on the outlet. And there are some pretty good reasons for that. It reduces process noise by allowing time for more mixing and for changes in phase. So particularly if you've got the steam and water being mixed, you got this problem of differences in phases. Bubbles to condense and droplets to vaporize. It gives it time for that to happen. If you have bubbles or droplets hitting that sensor, you got a very erratic measurement. So again, you want to make sure that you have a single phase. So far as temperature disturbances originating from within a reactor, the performance is about the same as for the inlet temperature control according to Shinsky. In Monsanto, though, the polymerization reactors are nearly always controlled by way of manipulating the outlet temperature, maybe because they wanted to see the start of one array reaction faster. Maybe they were more concerned about seeing the effect of some coating on the heat transfer surfaces. Anyway, it was predominantly in that way. Very high exothermic reactors had temperature control where the secondary loop was the outlet jacket temperature or coolant coil temperatures. Now let's look at putting a heat exchanger in that jacket recirculation line, and then you've got the you would have the lag associated with the heat transfer there, but you can really essentially eliminate from that from the control loop by throttling a bypass line rather than the chilled water line. However, there's the opportunity then to put in a valve position controller to optimize the situation in terms of having the right chill water flow. That always gives you a good flow here, and you can seek to actually minimize that exchanger bypass flow. And besides always making sure you have enough so you get this very fast response. It extends the rangeability of the system and can increase the heat transfer coefficient by keeping a high velocity going through the heat exchanger. And that can also even minimize what might be some fouling on the coolant side, although on the coolant side it's less likely unless you don't have a very good cooling tower water. Here we show the advantage of if you're going to have heating and cooling, the significant advantage of having a steam injection heater. So what you're really doing is, as you're going from cooling to heating, you're creating hot water. You don't have these two phases occurring. It's very fast. You don't have the heat transfer lags associated with heat exchanger, and you don't have a mixture of phases going on here. And so actually you could have had inlet jacket temperature control probably here and would have been fine. It creates hotter water, offering rapid heating and tighter control of the coil or jacket temperature with a smoother split range transition too. I mean, if you have two phases or you have heat exchangers and you're trying to make a transition from cooling to heating, man, it's really disruptive and really difficult in terms of making that to be not a problem in terms of tight control. And it seems to be often the biggest problem is split range points. And here, by using this control strategy, we've eliminated a lot of that split range problem. Of course, you still have to be concerned about the control valves, and when they go close and then they go open, you want to make sure that they do not have much stiction at the closed position. So again, you can make a very smooth transition and not get any stick slip going on, particularly since the stiction tends to be highest near the closed position. So stiction is very problematic. It's a split range point. So you want to make sure that's not an issue here in general. And for all split range control systems, no matter what type of control loop you're talking about. Minimize the stiction near the closed position. Okay, now we often have control being done by heat exchangers and a recirculation line. We have a temperature controller there and the process recirculation. It's probably going to get its set point from a vessel temperature controller. That's not shown here. So we're controlling the outlet temperature of the heat exchanger. Hopefully this is not a very long distance here from the heat exchanger to that elbow. But anyway, what we got shown is, again, throttling a bypass flow to get a faster response with a valve position controller being used to help optimize things in terms of greater rangeability and higher velocities going through the heat exchanger, and a lot of other benefits associated with this. And this is tuned so that it's gradual, although we'll get into the fact that you can get into being more intelligent about how you tune that valve position controller and use some PID options for it when we talk a little bit more about valve position control, say for reactors and distillation columns. So here we see the fact that we're controlling the exit temperature of the heat exchanger, and it has a self-regulating response, and it's pretty quick at this point compared to the vessel temperature. And this vessel temperature must have a much slower response because they have a cascade control system, and you want the primary temperature controller on the vessel to be much more slower and gradual, and then what we have in terms of recirculation temperature, which should be fast so that we have a good cascade loop where the secondary loop here being recirculation temperature is at least 5 times faster than the primary loop, that is the vessel temperature. And one of the challenges we get here in terms of tuning this temperature controller is that it has a self-regulating response in the short term, which is what you really want to concentrate on, and have it do its thing quickly and be tuned for that. But if you look at it long term, and particularly you have software doing this, and you have the test conducted for, you do make a step change, and you have the controller manual for, maybe more than a few minutes, but like an hour or something like that, you're going to see an integrating response. That can be very confusing, and you may try and tune for that, and that's not what you want to do. The integrating response comes from the fact that you've got coming back around through here is, of course, the recirculation going on. So you have an inlet temperature to this heat exchanger that's changing, and there's an integrating effect from the vessel volume. And so you don't want to be confused by that. Okay, this is a lot to be presented, but let's look at a kind of a reactor here that's very important in terms of it's and challenging because it has it's a situation where we want to make sure that the reactants are in the right ratio. We have a good resonance time for the reaction to go to completion, and the reaction rate typically has the best temperature associated with that, so we want tight temperature control. And so we got all these things at play here. Then we have shown in purple the fact that we have also some optimization going on here, and also some composition control going on here. We're trying to make sure that there's always some reactant available. So there's got to be a little bit excess reactant. And that's what this composition controller is doing here. If there was, if any of the reactant concentrations go to zero, the reaction stops. And then you've got, because you got a continuous situation here, you have the other reactant is flowing out unreacted, so you don't want that to happen. And there can be unbalances in the reaction ratios. If you change the production rate, one flow loop can respond faster than the other, one reactor flow loop than the other. And that temporary imbalance can cause an unbalance in the concentrations and can cause some concentrations that are not right to be flowing out. You got a continuous, so things are always flowing out here, and you don't want that to happen. So some people say, well, you should tune these flow controllers so that they have the same response time, so that if you're asking for a change in production rate, they both respond. But unfortunately, the same response time. But unfortunately, that means if you have one controller that's particularly slow, and I don't know why, maybe it's the type of measurement, maybe it's the type of valve, maybe it's because it's noisy and you got a bigger filter on there. You then make the other flow controller as slow as that. Now, that may seem okay, and that's commonly stated as the goal, until you think about, well, then what about pressure disturbances? You say you have the same set point in flow, but now you got to deal with pressure disturbances. I mean, that's one of the tasks of a flow controller, right? To deal with pressure disturbances. If you slow down the tuning of it, you reduce the ability for it to compensate for those pressure disturbances, or if the valve position isn't quite right. So you really want to tune these flow controllers for the best response on their own, as fast as they would do with a robustness, so it's not oscillatory. But in order to coordinate it, then you put a set point on the filter as you're going to change production rates. You can say, well, set points is bad in cascade control systems, but here we're talking about changing production rates. And you would have set points, equal set points. You don't want to get carried away with it. You want just a set point that makes sure that the slowest loop can follow that set point as well as the fastest loop. Now that's also going to be in place for reactant ratio control, but again, if you do it correctly and make it minimal, then you shouldn't have a problem. And you could choose to somehow do it just on changes in production rate and not in terms of correction for concentration changes. The important thing is always with filters that you be minimal in terms of the time constant. And here with reactants, We want smooth responses. Sometimes cascade loops, we say, oh, the secondary loop, we just want it to respond fast as possible. If there's an oscillation, that's okay, because that helps the primary loop get to do its job faster. But in terms of reactance, we don't want any temporary unbalances. We want a smooth response. So we don't want any oscillations. Now we also have a valve position controller here in purple, and it's going to try and maximize prediction rate based on looking at the makeup valve here, the coolant makeup valve, and saying, hey, we can produce more reactant here as long as that makeup valve doesn't go too far open. So as long as it's got enough room to take care of disturbances. So that's what it's going to do. It's going to kind of force that coolant valve to its maximum good throttle position with enough room to protect against disturbances, and do that by that valve position controller, ZC 1-4, adjusting, trimming the set point through the leader then of the reactant ratio controllers. And so I like the terminology of leader and follower. And usually there's one leader and there could be many followers. And so you have the production rate telling the leader what to do, and then the followers go in consistent with that. And you want the filters such that they can all work together in unison and not create any temporary unbalances. Now, we have the situation of a gas reactor, fluidized bed. And boy, this actually looks a lot simpler in terms of providing temperature control and also in terms of maximizing production rate. For a very fast reaction like this, and I'm saying, this is the residence time in here is a matter of a few seconds, whereas for the reactor, it's the liquid, it's minutes. But things happen so fast here, and it's so exothermic, typically in these fluidized bed reactors, that you can have the temperature control by manipulating the reactants. For a very fast reaction, short residence time, and high heat release, it prevents that inverse response in the manipulation of reactor feed rate for temperature controls. That is something that has been said, oh, you never want to do this, but they're really talking about the last case or vessels where you have a liquid reactants going on, and normally you don't want to have temperature manipulating reactants there, because you get into, if you have, typically say if it's an exothermic reaction, the operating temperature is higher than the feed temperatures, as you want to increase the reaction rate and increase the amount of heat release, and you increase the reactant flow, because it's cold, it's going to cause a drop in temperature. And that's noticeable in a liquid vessel type reactor. Here with this gas, it's not noticeable, and so you can get very good temperature control that inherently maximizes the production rate and based on the number of coils you have in service. So how do they change production rate here? They put more coils in service, and then this temperature controller is going to say, okay, I'm going, based on that cooling, I'm going to feed it as much reactant as necessary to get that temperature up to my set point. And again, as you're changing production rates, you want to make sure that they move in unison together, and so you have some minimal equal reactant flow set point filters so that you don't have to worry about the differences in the tuning response of these controllers to a type of measurement or type of valve or size of valve. Let's look at crystallizer temperature control. Temperature is critical for the operation of crystallizers in terms of getting the right crystal size and the number of the right crystals of the right size. So here we show we've got a temperature typically controlling the crystallizer, controlling the inlet temperature, because we are concerned, as I mentioned, about having particular restrictions on that inlet temperature. We don't want it to get too cold. Then it's going to cause crystals to form on the coolant surfaces, and then you get all kinds of problems. They're tiny, they're not the right size, and they start to coat the surface. All kinds of problems start to occur. So you have set point limits and restrictions on the inlet temperature of the coil here, and those little crystals forming, and coating clothes called frosting. Now for batch crystallizers, the cooling rate is initially low to prevent the formation of these small crystals. And as batch time increases and crystal size increases, then the cooling rate is increased exponentially at batch time, corrected by crystal size and density analysis. So here we show if you had an uncontrolled cooling rate, this orange or brownish orange thing here, it would start out very high cooling rate initially in the batch. Due to the temperature differences. And what we want in the beginning is much more gradual, so we can kind of program that into the temperature controller so that we don't have these tiny crystals and frosting occurring. And really, as the crystals have formed and we just want to then make them larger, and then we can go with higher cooling rates towards the end of the batch. Now for dryers, it turns out differential temperature between the inlet and outlet temperature, and I got a longitudinal dryer here, got a gravimetric feeder coming in here. Normally this would be shown kind of tilted down, because you want the product coming in here is going to come out, and you want it to come out here. And what we got is shown as a heat exchanger, heating the gas coming in, typically air, and it's kind of blowing these particles in here. Now this could be conveyor going through here, and we have the hot air coming in, mixing with it. And it turns out that if we just do some simple calculations, like doing an energy balance based on changes in temperature and taking into account, the physical properties and things we know about normal dryer particle size, and also the inlet moisture, we can do a pretty good inferential temperature calculation and have it corrected periodically by an outline analyzer or even an offline analyzer in the lab. And it turns out that most dryers that don't have this are over drying the product and wasting energy, and also losing out on the opportunity to actually increase production rate, because you are selling a little bit of water then, more water if you don't over dry the product. Now it doesn't sound right, but if it's acceptable within the product quality requirements, and in fact sometimes having product that's over dry can be a problem in terms of dusting. So having the right moisture in the product is a real opportunity here, and that most dryers are over drying. So a rather straightforward control strategy like this can be very, very useful. And here it shows that there's a constant drying rate going on until you got the interior moisture depleted. And now you have dry spots starting to appear on the surface of the particle. Then that reduces the driving force for heat transfer, or actually the the transfer coefficient, and and as a result, you get into this falling drying rate region, and and right down here, the particle is completely dry, and up here, the particle surface is completely coated with moisture, and so you can kind of take this into account as a kind of a predictable relationship. So after interior moisture, the particle is depleted, resulting in dry spots on the particle surface. The driving force for evaporation starts to drop, resulting in a falling drying rate that is proportional to surface moisture. And this is a key thing for batch operation. So if you were, instead of looking at dryer length here, by looking at batch time, and this was at the beginning of the batch here, and then at the end of the batch here, you would be seeing the effect of batch time on moisture, and you could take this relationship into account, have more intelligent dryer control. Now let's look at distillation column and how temperature is actually an inferential measurement of composition. And what you can do with simulations is make some step changes in the, say, the distillate to feed ratio. That's the most common thing. Or the reflux to feed ratio. And then you look at the temperature response. And you want to choose the tray with the largest and most symmetrical temperature response, and that's this green one here. So you would want to choose tray number 5. Now you could consider it with, what if you had chosen tray 13 that has a small response and it's quite non-symmetrical? Well, here we see dramatically what happens on, now we're in closed loop control. Before that was with the controller, it was a manual. We're choosing, well, maybe you don't even have a controller. We're looking at temperature responses. Here we've decided, oh, we have a temperature controller, and now we're going to have as process variable stage 7, and then compare what if we have as process variable stage 13 temperature. Well, we see with the solid lines the effect of controlling stage 7. Of course, if you're doing good control, it's right on at tray 7 here. We've got the temperature for both the feed decrease and feed increase are both right on here. But then we see that the deviations for the other trays are not that large. They're pretty good. And again, temperature being an indication of composition, we realize we've got tighter composition, pretty tight composition control here. When we compare it to the dashed line here, you know, if we look at tray 13 and just look at it, not knowing what's happening on the other trays, we say, oh man, we're doing good. In fact, it might look better in terms of the nearby trays. You know, you don't have much of an excursion. But look what happens here as you go to the lower trays. It's huge, the excursion, really terrible. So you don't want to be fooled into, you know, thinking, oh, you want the tray that's, you know, drawing the smoothest straight line. Actually, if it's not on control, you know, loop is in manual, you want the tray that's showing the biggest excursions in temperature, and hopefully, you know, in both directions. So we're going to look at some major types of control schemes, and there's 4 different control schemes we like to look at here for just a single temperature controller, where we're interested in controlling the top or bottom temperature, just one temperature controller. So we're not dealing with interactions. If you had 2 temperature controllers and you're trying to control both the top and the bottom temperature, then you got to deal with interactions. And I encourage you to go to the control talk column that I've done with Siegfriedo Nino, who's a protege of Shinsky, to show how he used relative gain matrices to find out how to decouple that and deal with the interaction problems you have when you're trying to control uh, two temperatures, and basically it's called dual temperature composition control, and you're getting into a lot of interactions going on then. So here we don't have so much an interaction problem, but we're trying to pair up the manipulating control variables. And if we have a top temperature being controlled, it can be simplified to the point of thinking about whether that distillate flow is really small or not. If it's a very small distillate flow, the level controller then can't really do its job by manipulating the distillate flow. It's just too small. So what it does is manipulate the reflux flow. And you want tight control for that, because what's going to happen here is the temperature controller is going to do its job by changing distillate flow now. And I've got feed forward. Feed forward is very important for distillation columns, because often the feed flow changes. The operator's making changes upstream, or there's a lot of parallel unit operations that then end up a common train of very large columns. So you have a lot of flow changes going on. You do the operator, do the parallel unit operations upstream. So you want flow feed forward. And what I've got shown in here is a flow feed forward signal. With the feed rate being the liter flow, and then making sure we ratio control the distillate feed in this case, and also the steam to feed in terms of the boil up for the column. But anyway, let's get back to the fact that temperature control is manipulating the distillate flow. In order for that to affect the column, it has to be done by means of the level controller, because it changes distillate flow. That doesn't affect the column until the level changes here. And it's not going to change that much, particularly if it's a horizontal receiver here. So this level controller has to respond to very tiny changes in the level, and you need a very sensitive level measurement as well. And maybe this horizontal drum is not really the best situation, because you have a huge change in flow rate before you see much of a over a period of time before you see much of a change in level, because it's a horizontal drum. You need a very sensitive level measurement. I would say for tight level control, you probably want to go with radar, something like that. Anyway, tight level control, which then says, oh, the level changed to the distillate flow changing because the temperature controller wants to affect the column, and it does that by way of the reflux flow. I'll do my job. The level controller says I'll change the reflux flow. Now, you can use feed forward from distillate to reflux to make that happen sooner. But you still need tight level control, because there is an internal reflex control that is being done here. One of the inherent advantages of this control scheme is, as there's temperature changes to the column, and often these columns are so large, they're not insulated. I don't know all the reasons why they're not insulated, but that and the overhead lines are not insulated. So you have this common problem where you have a very cold, wet rainstorm come in, and you have a drastic difference in terms of the temperature of what's coming overhead, and maybe even the amount of vapor that's coming overhead, and also the temperature of the reflux coming back. And it turns out that this level control inherently compensates and changes this reflux flow in the right direction to deal with that. And it has the inherent decoupling of the energy and material balances. The disadvantage here is the slower control of bottoms composition, and that could be problematic for stripping columns where they're typically interested in controlling the bottom composition. And there's a dynamic compensation required for feed forwards here, so that's something you need some software to help you with typically. Because if you got a feed change coming in here, it'll arrive at that temperature control point at a different time than when the reflux does. So you need to make the reflux arrive at the same time that the feed flow change. The change in reflux flow arrive at the same time as the change in feed flow at the temperature control point through dynamic compensation of feed forwards. Now for column strategy number 2, we have a situation where we have a large distillate flow. The level controller can manipulate that, and now the temperature controller can go ahead, and it kind of takes a roundabout approach here, but comes back and actually manipulates directly reflux flow. We get faster temperature control since it's independent level control. We don't have that internal reflux control like we had with the other one. And we have some moderate interaction between the energy and material balances. So if you're doing top column temperature control, I kind of favor the first control scheme. Notice here in the second control scheme, we want loose level control because the level control is not really doing anything in terms of composition control. It's just controlling inventory, and it's going to upset the equipment downstream if it's making very fast changes, abrupt changes. So you want sort of what do you call maximum absorption of variability in terms of level. I call it minimum transfer of level changes to the manipulated flow. And you can do that through some intelligent tuning, which we've covered in other WebExes. So you want loose level control. You've got to be careful, though, that if you just decrease the level control again, you're going to most likely get into very slow oscillations, and that's not good at all. And that occurs often, we'll see, for temperature control systems. You just don't want to decrease the level controller gain. You get into oscillate unless you've greatly increased the reset time. Okay, column number 3 here. Now we're dealing with the fact we're controlling at bottom temperature, and here in this case we have a large bottoms flow, so the level controller can do its job. And again, it's loose level controller because it's not affecting the composition in the column, but it's affecting the downstream unit operations where the bottom flow is going to. The temperature is controlled by manipulating steam, the boil up, and it provides very fast temperature control because you can change that boil up through the column, very quickly, and in the matter of maybe less than a minute, whereas it could be hours changing the column composition by changing reflux flow. Relative disadvantages: severe interaction between energy and material balance, and possibly less process sensitivity from the manipulation of vapor rate. Normally, the manipulation of vapor rate, also called manipulation of separation, doesn't have as great a process gain and process sensitivity in terms of what you're trying to do. And then the last control scheme is, what if you have a small bottoms flow or you can't do level control? So now you're forced to do level control by manipulating steam, but now you got inverse response, and you need tight level control because the temperature controller is changing the bottoms flow. You really don't see the effect on the column until that is seen as a change in level, and then the level controller has to do its job to actually change the boil up. But how do you do tight level control if you have inverse response? It's really quite a challenge. So you have to rely particularly on feed forward here. A relative advantage is fast temperature control if level control is tight, but this may not be possible due to level inverse response. Good steam to feed ratio control is critical. Relative disadvantage is moderate interaction between energy and material balance, and possibly less process sensitivity from the manipulation of separation vapor rate, just as we saw with the other control scheme for bottom temperature control. Now, a problem that's very common for temperature on large volumes is the fact that there is, for continuous processes, for a large liquid volume, a near integrating response. And that means is it has such a large time constant associated with the liquid volume, typically a vessel or distillation column, that in the short term, it looks like it's ramping, like it was an integrating response, like we get from level. And the problem you get into with this is that if you are cautious about using the maximum PID gain, which often is the case because the maximum PID gain, particularly for well-designed, liquid, well-mixed, stirred reactors, can be as high as 25, 50, or more. I've seen 75. And people are not used to that. So they say, oh, a gain of 75. Well, I can't do that. I'll use a gain of 2. And they do that, and oh boy, they're actually they're at, well, they're worse than this. Let's say, okay, they gain to 75, and they say, oh, well, let's say the gain starts out, it really should be 50, and just so we can work with numbers better. And then they say, oh well, I can't do 50. Maybe I'll do um, uh, maybe I'll do something smaller than maybe uh, maybe 20. And then they're at this, and they're getting an oscillation. They say, "Oh, I got too much gain. I know I didn't like that gain being that high." And so uh, then they go down, okay, and they go down a gain of 10. Oh, it's bad. Oh, geez, I don't know what's going on here, but I know from control theory that high gains cause oscillation, so I'm going to decrease the gain. So they go down to a gain of 5, and now the oscillations are worse. They're completely perplexed. They don't know what to do. Really, the solution was to go with the gain of 50, and then they had tight control. Not only are these oscillations here bigger in amplitude for a low gain rather than a high gain, and I didn't show you the high gain situation, but they're much faster for high gain and more effectively filtered out downstream. They're a lot smaller for a high gain than they are for a low gain. So you get into these very slow, large oscillations that are not very well filtered out by downstream volumes. And you see how it's counterintuitive this is. And what you really needed to do, if you couldn't stand that gain of 50, you needed to increase the reset time by at least a factor of 10 or more. And that's something people are not used to doing. You know, the reset time maybe already should be like 1,000 seconds, and they would have to go with 10,000 seconds, and people just are not accustomed to doing that. And then we have integrating processes if we have a batch operation, say for temperature, and the problem is even worse. And if we get into highly exothermic reactors, that can be runaways. And I know technically they should never be designed for that, but for very high polymerization rates, there can be operating regions. I've seen it where it is a runaway, and you can't have enough cooling, and it blows over to the flare stack. Anyway, for runaway processes, and this can be kind of understandable, that you get into low PID gains, you really got into a safety problem because the only feedback there is through the PID temperature controller. The process itself is running away and has this positive feedback going on, accelerating things. And the only way for you to deal with that is to have more aggressive feedback action through the PID controller gain. And you want to really make sure the reset time is very large. In fact, my experience was with these highly exothermic polymerization reactors, they wouldn't even allow you to use reset time. They were proportional plus derivative control. It's very high gain. And the offset, probably not realized that the offset from set point, if you don't have any integral action, is the offset is inversely proportional controller gain. So if you have a very high gain and you have a very tiny offset from set point, and you really don't need integral action. And that's the principle, actually, of a good valve position controller by maximizing the gain. Some of the gain settings, don't give you the true gain. The true gain in a well-designed, well-tuned valve positioner has a gain of approaching 100. And that means you really don't need integral action in the positioner. In fact, it causes all kinds of problems. And so the offset is very tiny, and really want for offset. It will be corrected by the process controller, and it has really no consequence, and it's very tiny. So don't ever turn on integral action in a positioner. That's a subject in itself. Best practices. So we're going to summarize everything very quickly here. Use RTDs if within the RTD temperature range and there's no excessive vibration. I didn't mention the fact that RTDs are notoriously more sensitive vibration, but if you have a good thermal well and you pay attention to guidelines, that should not be an issue. Avoid if possible ceramic protection tubes and low thermal conductivity thermal wells. Use tight-fitting, stepped, or tapered thermal wells. Tapered have a higher pressure rating. Seek thermal wall lengths to diameter ratios that are greater than 10 to 1. Now, if you have a tapered or stepped, I think you might need to get into averaging that diameter to get kind of what the guideline would be over the insertion length. Use spring-loaded tip-sensitive sheath sensors. Spring-loaded, make sure that tip's sitting in the very bottom thermal well. Ensure insertion length minimizes conduction error and minimizes profile error. The profile error in pipelines is much greater than I realized, and for polymers, it's really horrendous. Seek liquid and gas velocities greater than 0.1 and 1 foot per second, respectively. And I would say that's kind of the minimal, particularly for gas. Locate to maximize phase, velocity, uniformity, but minimize dead time. But if I had to take more dead time to get the fact that we don't have phase problems or don't have too low a velocity, or we make sure we don't have mixing problems, I would go with the greater dead time. Use smart transmitters mounted close to, if not on, the thermal well. Use RTD sensor matching via the CVD equation to greatly improve accuracy. And now to say that some of the smarter input cards do allow you to enter coefficients individually for a sensor. It used to be you had to only get that through a transmitter. Use minimal equal set point filters and ratio control of reactants, particularly when you're changing production rates. Program crystallizer temperature and minimize cooling rate at the start of a batch. Use delta temperatures for inferential moisture control of dryers. And choose the column tray with the largest symmetrical change in temperature for temperature control. Maximize temperature controller gain. Maximize temperature controller reset time. Seconds per repeat, minutes per repeat. They don't say per repeat, they probably just say seconds, minutes. So we're talking about very large settings for that, particularly if we're talking about liquid reactors, and if we're talking about columns, oh my gosh, that reset time's got to be huge if we're manipulating, say, the reflux or distillate flow rates. If you're manipulating the vapor rate for temperature control, the boil-up rate, then the reset times are going to be a lot less, because the response to changes in boil-up is so much faster. I encourage you to read more about it, and here's a book that I've updated a few years ago, and I do have some updates on the figures and one correction to the table. It's kind of obvious in terms of air gap. There was one air gap that was entered that was missing a zero, and therefore was way off in terms of where the decimal point should be. Questions? Now, I got a couple of questions. One was from Dennis Becker, and he said, well, why can't we use RTD and thermocouple input cards? Because we are saving a lot of money. And you got to look at the fact that the span for particularly thermocouple cards are huge, and the percent accuracy is normally in terms of percent to span. And so you have inherently a much larger error associated with an input card. You really want to customize the span to be as narrow as possible, and you can do that through a transmitter. Transmitters also have better resolution, less of an issue today. Back, a couple of decades ago, the DCS system resolution, well, seemed like it was okay, maybe 12-bit A to D. When you translated that to a thermocouple card range, you were getting steps of maybe a quarter of a degree just due to resolution error, and that just played havoc with the temperature controller. Particularly, you couldn't use derivative action. Temperature changes are really gradual and small, especially if you're trying to do tight control. And here you have these steps of a quarter of a degree, and you couldn't use the derivative action, and you couldn't use as much gain as you wanted, and you really had horrible control, particularly if you're trying to control within a few tenths of a degree. Now, with the newer DCS cards, it's less of an issue, but you still don't have the diagnostics, and you don't have the ability to individually calibrate as well like you would with a transmitter. So I favor transmitters. And you don't have the extension lead wire errors and the cost of the extension lead wires. You should have premium thermocouple wire to eliminate the errors associated with that. And for RTDs, you should add 4 wire extension wires. And 3 wires you might be able to get by if the RTD is not that far away from the control room, but typically it's not. You can't generalize with that, so you need 4 wires as your extension wire for RTDs to do the compensation for changes in resistance in that lead wire. Otherwise, you're going to lose that phenomenal RTD accuracy. Now, it turns out that you can get the CVD equation coefficients entered for RTDs. So that's less of an issue with certain of the newer input cards, the RTD input cards. I had another question, and how do you know if your controller gain is too low? Well, the thing I suggest doing is well, it'd be better if you had a simulation, some intelligence, dynamic simulation, some intelligence as to what the PID gain should be. And also you should do some testing. You should have software that allows you to do testing to determine what are the dynamics, and it'll tell you what the tuning setting should be. And if it says the PID gain should be 50, you're going to have to go with 50, or else you're going to have to drastically increase the reset time. So the best solution is to go with tuning software and realize that if you don't use that gain as suggested by the tuning software, and you start decreasing because the operator says, oh, I don't like to move around my temperature controller output, and the process engineer may say as much. You realize then you're going to have to make a corresponding great increase in the reset time. Now, there's also an option I didn't talk about here for valve position control, and also for this concern about high gains. If you have the enhanced PID where you have external reset feedback, you can put a rate limit on what you're manipulating. And what you're manipulating could be a valve position, or it could be a set point to a flow controller. And or even a secondary temperature controller. Anyway, you can put on set point rate limits, and then you turn on external reset feedback, and it says, oh, I realize you don't want to move things that much, but if you have a big upset, I'm going to do what I can that you allow me to, that you can respond to. And so you don't have to back down on the controller gain. You won't get into this situation where the controller gain is too low for the reset time, and it even protects you against a situation we expressed a little bit of concern about, that hopefully is not usually going to enter in normally with you, but cascade control systems where the secondary loop is not fast enough. By having external reset turned on, it realizes, oh, that's secondary, and you're feeding back the actual process variable of, say, the flow controller process variable. Or if you got a valve, enabling valve, I forgot to mention this, you got to have a fast readback of that valve position as the external reset feedback. You do that, and then the controller is going to automatically recognize, I can't drive the output faster than what I'm manipulating is responding. A very great benefit. And you can, for valve position control, you can have a gradual optimization going on, and a fast getaway for abnormal situations. This gives you much more intelligence in terms of your valve position or controller tuning. The other thing you can do is, okay, you don't have the tuning software readily available right now, or you just want to make a quick check. What you can do is increase the reset time, and I would say by at least an order of magnitude, and maybe 2 orders of magnitude, because it's generally going to be safer unless you're dealing with some set point changes going on here. That so if it's a relatively calm part, there's no part of the process operation, there's no big set point changes, no big disturbances coming in. So you can really see what's going on anyway due to reset action. If you increase the reset time by an order of magnitude or 2 orders of magnitude, things will be actually more stable. They may not respond as well to your demands for set point change or to disturbances, but it will be more stable. And if these oscillations go away, and it may take, if these are very slow oscillations, which they tend to be, then if they go away, you know that, oh boy, it was due to the fact the controller gain was too low. Now you have an option, well, if I want to keep that low controller gain, I'm going to have to leave my reset time so much larger, and then you can kind of home in, is it a factor of 10, is it a factor of 100 times larger reset time than I need? Until you actually get the tuning software going and you have the opportunity to do those tests and get the right tuning settings. The other thing as a diagnostic, if those oscillations are dying out, if you kind of look at enough trends and see that the oscillations do tend to die out, but their period is like 40 times the dead time, as what I showed there for those test cases. It's probably due to the fact that you're violating that low PID gain limit. And, normally oscillations, if it was due to too aggressive gain action, would be more like, 4 times the dead time. So here, it's 40 times the dead time. The period of oscillation is 10 times larger than what you would get if you had oscillations due to too high a PID gain. So that's a clue that it's due to the fact you have too low a PID gain, and you're now much more sensitive to the integral action. Now, in previous WebExes, we showed, I think it was on PID options and solutions and features, that what we want to do as a check is to make sure that the product of the controller gain and reset time is greater than the inverse of the integrating process gain. And we can come up with an integrating process gain, whether it's near integrating, true integrating, runaway, based on the ramp rate. If we make a step change in the output. And we look at this initial ramp rate, and we take that ramp rate in terms of percent PV per second and divide it by the percent change in controller output that we made. We have the integrating process gain, and we only need to look at that, maybe for 5 dead times. It doesn't have to be, the maximum ramp rate we see that's consistently in the right direction, over a period of about 5 dead times. That can give us a good estimate of what the integrating process gain. You got to do it though in terms of percent of scales, because that's what the PID controller is dealing with. Its algorithm is in percent. And if you're manipulating, say, a secondary temperature, say to a jacket inlet or outlet, then it's percent of the secondary temperature controller scale. So again, scales are very important, and make sure you're dealing with percent per second per percent. And it turns out the percents kind of cancel out then. And what they often state for integrating process gains is not percent per second per percent change in your manipulated variable, but is simply 1/seconds. Now, your reset time then needs to be in seconds if you're doing an integrating process gain. That is 1/seconds.